Well, hello, ladies and gentlemen. Let's continue on with our treatment of the first law of thermodynamics for a closed system. So today's topic will continue on and do another example. We did plenty of examples last time, so maybe we'll keep the lecture a little bit short today. We'll do one example involving a two-phase system with H2O as the fluid. We'll be heating up a gas liquid mixture, saturated mixture, and determining how much time it takes to heat up a mixture of vapor and liquid using an electric heating element. That'll be the plan for today. But so we'll do this example, and then we're going to move on to what's called the du-dh property relationship. We're going to revisit specific heats. Remember CV and CP that we defined earlier about a week ago, back in chapter 3? Well, we're going to use specific heats and get the full power available with the concept of specific heat and use it to derive equations that allow us to calculate the change in internal energy and the change in enthalpy for a system using specific heat. So we're going to derive some relationships that allow us to calculate the change in internal energy and enthalpy of a system using specific heats. Pretty neat stuff. So let's proceed here for our example. We have we have initially a two-phase system composed of 25% quality, 25%. So this is H2O with a quality of 25%. So basically by mass, we got saturated vapor and saturated liquid in a container. Liquid vapor in a container. Now this is a rigid container. It's a rigid container, and inside of it is a heating element or a resistor through which current passes. So we have a little heating element here. There's a voltage difference across the wires, delta voltage, and then there's a current passing through the wires. So we got electric work or electric power being done on the H2O in this rigid container. So let's go over the details a bit more here. There's 5 kilograms of H2O inside the container. The initial pressure is 100 kPa, so approximately 1 atmosphere. As I said previously, the quality at state 1, the initial quality of the H2O is 25% vapor by mass. And then, of course, we have the heating element. A current of 8 amps flows through the heating element, and the voltage difference across the wires is 110 volts. So basically, household mains voltage. So this rigid container initially contains a mixture of H2O, liquid and vapor. The heating element is turned on. We dissipate energy. We heat up the H2O until all of it becomes a saturated vapor. So state 2 is a saturated vapor. So quality at state 2 is equal to 1, all right? So what are we supposed to find? Let's find out how long, delta T, how long it takes to boil away all the liquid and to get a saturated vapor in our rigid container. Okay, so this is a bit different problem than what we've been used to before. Previous problems used either an ideal gas, so we're able to use the ideal gas law and to use ideal gas property tables. This problem involves H2O and it involves a two-phase mixture. So we're going to have to use saturation tables to calculate change in internal energy and such. It also has time in here, delta T. We're not calculating a heat transfer rate or a total heat transfer or a work or something. We're calculating time required to boil away the liquid H2O. Okay, liquid H2O, and get saturated vapor. So let's get started here. We'll write down our assumptions as we go along. So that's why I have the assumptions section on the next board. We'll write the assumptions down as we go along. Okay, so let's begin the analysis here. So we're looking for a time required to undergo some process from state 1 to state 2. If you like, let me put up a TV diagram showing what's going on as well, so we have an idea what's going on. So here's our saturation dome. So we start off with equality. So here's we start off with a certain, here is our isobar. We start off with a certain pressure P1, and this is our state 1 right here. 25% mixture. Now, what's the process look like? We're going from state 1 to state 2. Let's go back to the problem statement. So we have a rigid tank undergoing some sort of isochoric process where we're boiling away the liquid H2O. If it's rigid, what kind of process is it? It's isochoric. Rigid tank, that means isochoric. So I'm going to put up here in the assumptions, isochoric process. By the way, before we get too far into it, let me define my system here. So my system is going to be the H2O in the container. H2O in the container. Basically, what's happening with the electric heating element is we have an electric work interaction going on due to the heating element, okay? Okay, isochoric process until we get to a saturated vapor. So we're moving up here, and then that is state 2. Okay, and there's an isobar that goes through here. It's an isobar that goes through there. So there's P2 right there, okay? That's what the process looks like. That's what the process looks like. You know, that should be horizontal. That doesn't look good. That doesn't look good. Okay. There we go. Good enough. State 2, good enough. Okay, so that's the process. To calculate the time required to boil the liquid away, let's write the energy balance. Let's see what we get. But what version should we write up? We're interested in time. So maybe we should write the rate-based. Let's write the rate-based energy balance. Let's see here. Q dot minus W dot is equal to the time rate of change of total energy. Okay? That's the E balance for a closed system. Now, there's nothing in the problem statement about heat transfer. In fact, if I don't assume a heat transfer 0, there's nothing about it. If I don't assume heat transfer 0, I cannot calculate delta T because I don't know what Q dot is. I know what the work is, the electric work. It's a voltage times a current. So I think I need to assume away the heat transfer rate. So let's assume it is a insulated container and Q dot is equal to 0. I'm going to put insulated. Insulated container, okay? So I'm going to assume Q dot is equal to 0. What's the W dot term? Well, we know we have some electric work. No shafts, no propellers inside this tank. No shaft, no propellers, so there's no shaft work. It's a rigid container, so volume is constant. It's an isochoric process, so boundary work is 0. So electric work is equal to the work. I'm going to write here, W dot is equal to W dot electric. It's an isochoric process. We're assuming it to be isochoric. No shafts in there, so I think that's a good assumption. W dot electric. Okay, that's what W dot is. Now, total energy, of course, is equal to DU. I'm sorry, total energy is U plus PE plus KE. So this DE dt is the change in internal energy plus the change in potential energy plus the change in kinetic energy of the system. Okay? And of course, you can go through and take these derivatives and you get du dt plus dpe dt plus dke dt. Now, the dpe and dke dt terms, they're due to a change in velocity or speed or a change in position of the system, i.e. gravitational potential energy. I don't see any indication that the rigid container is moving, accelerating in any way. So I'm going to assume away changes in potential energy and kinetic energy. So I'm going to write here PE is equal to KE and equal to a constant. Well, they're both, I'll tell you what, I don't write that. Let's not write that. PE and KE are equal to constants. Okay? That means they're not changing with time. 0. Okay, so all I'm left with is du dt. Let's write my final energy balance here. I got negative W dot electric is equal to du dt. Okay? Okay, we got a differential equation here, and I want to get a delta time T2 minus T1. I want a delta time or a change in time over the process. How do I get that out of this equation? Well, I'm going to multiply both sides of the equation by dt. Okay? So I got minus W dot electric dt, and then I'll have equal du. Okay, so I just multiply both sides of the equation by dt. Now let's integrate over the process. Integrate over the process. Let's see here. In the first integral involving W dot electric, the variable of integration is time. So over the process, we're going from T1 to T2. On this side, we're taking the variable of integration as internal energy. So from state 1 to state 2, we're going from U1 to U2. Okay? Now, the integral on the right is pretty easy. The integral of du from U2 to U1, or U1 to U2, that is U2 minus U1. Okay? That's the right-hand side integral, U2 minus U1, or delta U from 1 to 2, if you like. The left-hand side integral, well, the assumption here is the electric current's constant. So this is a current, and the voltage is constant. So the electric work is a current times a delta voltage. And this is the constant. So this voltage times current is constant. So W dot electric is constant. I can pull it out of the integral. And I get negative W dot electric integral dt from T1 to T2. What's that integral? Integral of time, d time from T1 to T2. That is delta T, or T2 minus T1, if you like. So this guy here, this is delta T from 1 to 2. Okay, let's write what we have. Let's write what we have. Negative W dot electric delta T from 1 to 2 is equal to U2 minus U1. Or if you like, delta U from 1 to 2. But I'm going to write U2 minus U1. All right. Okay, so we're interested in the delta T, the change in time, or the time required to boil away the fluid. That's equal to U2 minus U1 over negative W dot electric. Okay? If you're wondering what we're going to do about this negative side here, remember the electric work or power is being done on the system. So this W dot electric will actually be negative voltage times current. Okay, so the negatives will cancel out and we will get a positive value for delta T. All right? Okay, so let's see what we got. Okay, I basically know what W dot electric is. That is negative current times voltage. I have both these things. Okay, so I have W dot electric. What about U1 and U2? What about U1 and U2? Well, U1 and U2 are mass times the specific internal energy at state 2, and mass times the specific internal energy at state 1. I know the mass. I don't know the specific internal energies at state 1 or state 2. In fact, let me rewrite that equation right here. I'm going to make my substitutions here. So let's write the equation one more time. Mass. Let me put the U1 and the U2 together. And then I have negative times a negative, or positive voltage times current times delta voltage. Okay? And again, I have delta voltage, I have current, I have the mass. I need to find U1, U2. All right? Okay, let's see how we're going to do that. Let's see how we can find the voltage. I'm sorry, the state U1 and U2. Okay. Let's see if we can find U1 and U2. Let's see if we can find U1 and U2. Let's see here, U1. That's equal to, we have an initial pressure, we have a quality. So U1 is equal to the specific internal energy of the saturated liquid, evaluated at 100 kPa, which is a bar, plus the quality at state 1 times, oops. I'm going to actually, hold on a second, I need to break. I'm going to break the lecture here.